October 15, 1942. 08:47 hours. Naval Technical Research Institute, Kamakura, Japan. Lieutenant Commander Takeshi Miyamoto stood in the examination hall as two enlisted men carried in a metal crate marked with American military stenciling. Rain drummed against the corrugated roof, but inside, the silence was absolute. The crate contained something that would change everything Miyamoto thought he knew about the war. A captured SCR-268 radar system, recovered intact from a downed American reconnaissance aircraft near Guadalcanal. Miyamoto was one of Japan's top electronics engineers, holder of degrees from Tokyo Imperial University in electrical engineering and physics. He had spent the previous 2 years developing Japan's first operational radar systems, working 16-hour days to give the Imperial Navy the electronic eyes it desperately needed. He had expected American radar to be crude, perhaps equal to Japanese prototypes from 1940. Intelligence reports suggested the Americans were fumbling with large, unreliable systems that barely functioned in combat conditions. The crate was opened. Inside, secured by foam padding, sat a compact radar transmitter-receiver unit that looked nothing like what Miyamoto had imagined. It was smaller than Japan's current operational systems, yet the construction quality was immediately apparent. Precision-machined components, standardized parts designed for mass production, weatherproofing that suggested this was not a prototype, but a production model deployed in thousands. Captain Yoji Ito, Miyamoto's superior and head of the Naval Radar Development Section, stood beside him. "Begin the technical examination," Ito said quietly. "Document everything. I want specifications, manufacturing analysis, component evaluation, and comparison with our current systems. The High Command believes we're ahead in electronics. Let's see if that's true." Miyamoto approached the radar unit with growing unease. Even from visual inspection, before any measurements or testing, something was wrong. The Americans weren't supposed to have this. The compact magnetron visible through the access panel was operating on wavelengths Japan was still struggling to achieve in laboratory conditions. The power output indicators suggested performance far beyond Japanese operational systems. He looked at Ito. "Sir, this is a 10-centimeter wavelength system." "Test it," Ito replied. "Then we'll know." What Miyamoto would discover over the next 6 hours would not just reveal American technological superiority in one area. It would expose a truth that some in Tokyo already suspected, but refused to accept. Japan was fighting an industrial and scientific war it had already lost. The numbers, the specifications, the manufacturing capability visible in this single captured radar unit would tell a story more devastating than any battlefield defeat. And Miyamoto's detailed technical report, completed 3 weeks later and forwarded to Naval High Command, would be quietly filed away, marked "Assessment Too Pessimistic, Never to Influence Strategic Planning." But reality doesn't care about optimism, and radar doesn't lie. Miyamoto's team began with the magnetron, the heart of any radar system. The American magnetron operated at 10 centimeters wavelength, producing 10 kilowatts of peak power output. Japan's best operational radar, the Type 21 air search system, operated at 150 centimeters wavelength with 5 kilowatts peak power. The difference was staggering. Shorter wavelengths meant dramatically better resolution and accuracy. He measured the magnetron's efficiency, 48% conversion of electrical input to radio frequency output. Japan's best laboratory prototypes achieved 28%. This American unit was mass-produced, standardized, installed in aircraft across the Pacific, yet outperformed Japan's most advanced experimental systems. The receiver sensitivity was next. The SCR-268 could detect aircraft at 35 kilometers with a minimum detectable signal of 98 dBm. Japan's Type 21 radar detected aircraft at 22 kilometers with 85 dBm sensitivity. The American system was 20 times more sensitive, able to detect weaker reflections at far greater distances. Miyamoto examined the display system. A planned position indicator showed targets as bright dots on a circular screen, giving operators instant situational awareness of all aircraft within range. Japanese systems used A-scope displays showing only range, requiring operators to manually rotate the antenna and plot positions by hand. The American system gave complete tactical picture in real time. The Japanese system required skilled interpretation and manual plotting that took precious minutes. "Lieutenant Nakamura," Miyamoto called to his assistant, "bring the specifications for our latest Type 22 surface search radar." Nakamura returned with a folder. Miyamoto compared. Type 22 operated at 10 centimeters wavelength, matching the Americans, but maximum range was 25 kilometers for ship-sized targets. The American system, designed for aircraft detection, achieved 35 kilometers. For surface targets, American SG radar systems reportedly detected destroyers at 24 kilometers, cruisers at 35 kilometers. The manufacturing quality was what disturbed Miyamoto most. Every component showed precision machining, standardized parts designed for interchangeability. The waveguides were formed with uniform wall thickness of 1.2 millimeters. Japanese waveguides varied by 0.3 by 0.5 millimeters due to hand forming. The American unit used standardized vacuum tubes, the 6J4 triode, the 6SN7 dual triode, tubes manufactured by the hundreds of thousands. "This isn't a prototype," Miyamoto said to Ito. "This is a standard production model. They're making these by the hundreds." Ito's expression didn't change. "Continue the examination." Miyamoto tested the antenna system. The parabolic reflector achieved 28 decibels of gain, focusing radio energy with exceptional efficiency. The antenna rotation mechanism used ball bearings with tolerances of 0.05 millimeters, ensuring smooth rotation without vibration that would blur the display. Japanese systems used sleeve bearings with 0.2 millimeter tolerances, acceptable but inferior. The power supply was a revelation. The American radar operated on 28 volts DC or 115 volts AC with automatic switching and regulation that maintained stable voltage within +2% despite varying input. Japanese systems required 100 volts AC with manual adjustment, voltage fluctuations of +10% affecting performance and reliability. "Sir," Miyamoto said carefully, "every subsystem is superior to our equivalent, not by small margins, by factors of 2 to 3 in critical parameters, and this appears to be a standard field unit, not their most advanced system." Ito was silent for a moment. Perhaps this was captured from a specialized reconnaissance unit, an experimental installation. Miyamoto pointed to the production markings. "Serial number indicates this is Unit 2847 in the production run. The date stamp shows manufacture in June 1942, 4 months ago. They've produced at least 3,000 of these systems in 1 year." He didn't say what both men were thinking. Japan's entire radar production in 1942 would total approximately 600 units of all types. The Americans were producing more of this single radar model in 1 month than Japan produced in total across all designs. The examination continued through the afternoon. Each test revealed the same pattern: systematic superiority in design, manufacturing, and performance. The Americans hadn't achieved one breakthrough that Japan could replicate. They had achieved comprehensive technological and industrial superiority across every aspect of radar development. By 1700 hours, Miyamoto had compiled 2 pages of specifications. He looked at the numbers and felt something he had never experienced before in his engineering career: the absolute certainty that Japan was fighting an enemy it couldn't match technically and therefore couldn't defeat militarily. "Begin the detailed component analysis," Ito ordered. "I want to know how they achieved this." What they discovered next would be even worse. Day 2 of the examination focused on the radar's integrated fire control system. The SCR-268 wasn't just a detection device. It was designed to guide anti-aircraft guns with precision tracking. Miyamoto measured the tracking accuracy: 0.5 degrees in azimuth, 1.0 degree in elevation, maintained while tracking targets moving at 450 kilometers per hour. Japan's experimental fire control radars, still in development, achieved 2.0 degrees azimuth accuracy at best. The Americans had integrated automatic tracking. Once an operator designated a target, the radar locked on and followed it automatically, feeding continuous position data to gun directors. Japanese systems required manual tracking, operators physically rotating the antenna to follow targets, introducing human error and lag time. Miyamoto examined the computing mechanism that translated radar data into firing solutions. A mechanical analog computer, compact and ruggedized for field use, calculated target velocity, altitude, and predicted position. It output gun elevation and azimuth angles directly to gun mounts, updating 10 times per second. Japan had nothing comparable. Japanese gun directors used optical rangefinders and manual calculations, requiring 30-45 seconds to generate firing solutions that were obsolete by the time guns actually fired. "Lieutenant," said Nakamura, examining the power supply section, "look at this voltage regulator. It uses negative feedback stabilization with 3-stage amplification. I've never seen this topology in Japanese designs." Miyamoto studied the circuit. The Americans had implemented advanced feedback control that maintained rock-solid voltage regulation despite varying loads and input fluctuations. It was elegant, efficient, and far beyond current Japanese practice. This level of circuit design suggests advanced theoretical understanding and extensive testing. They didn't stumble on this configuration. They engineered it systematically. The third system examined was the IFF transponder, identification friend or foe. When interrogated by friendly radar, the transponder automatically broadcast a coded response, instantly identifying the aircraft as allied. The system operated on different frequencies than the main radar, using separate transmitter and receiver with automatic synchronization. Japan had no equivalent system. Japanese aircraft identification relied on visual recognition, radio communication, or pre-planned flight corridors. In the chaos of combat, this led to friendly fire incidents. The Americans had solved this problem with automatic electronic identification that worked beyond visual range in any weather conditions. Miyamoto began testing the IFF transponder's specifications. Operating frequency, 157-187 MHz. Response time, 3 microseconds. Coded response capacity, 64 different code combinations, changed daily according to classified schedules. Range, effective response to interrogation at 48 kilometers. "This is standard equipment," Miyamoto said, reading the installation manual included with the captured system. "Every American aircraft has this. Every American radar station can interrogate and identify aircraft automatically at ranges where Japanese observers can't even see targets." The pattern was clear now. The Americans weren't just ahead in radar detection. They had developed integrated systems where radar, fire control, aircraft identification, and tactical communication worked together seamlessly. Each system reinforced the others, creating combined capability far exceeding the sum of individual components. Miyamoto examined the production quality of the IFF unit, printed circuit boards with standardized component layouts, modular construction, where entire sections could be replaced in the field without specialized tools or skills, weatherproof sealing using advanced rubber compounds that remained flexible in temperature extremes. Every design choice reflected mature engineering practice and extensive field experience. Japan's radar systems, by contrast, were hand-built, each slightly different from the last, requiring skilled technicians for any repair. Component failures meant complete system replacement because parts weren't standardized. Reliability was poor. Japanese radars averaged 30-40 hours mean time between failures. The American system's maintenance log, recovered with the unit, showed 180+ hours of operation without failure before the aircraft was shot down. "Captain Ito," Miyamoto said carefully, "we need to examine American radar production capacity. These systems show design maturity that requires years of development and testing. The manufacturing quality suggests large-scale industrial production with sophisticated quality control. If they're deploying these systems widely, the numbers could be—" He trailed off. Ito's face was expressionless. "Write your assessment. Include all specifications and comparisons. I'll request intelligence data on American production." That night, Miyamoto couldn't sleep. He kept seeing the numbers, the specifications, the manufacturing quality. Every measurement told the same story. Japan was facing an enemy with technological and industrial capability that exceeded Japanese capacity by margins that could not be closed. Not with harder work, not with greater dedication. The gap was too large, growing too quickly. 3 days later, the intelligence report arrived. What it revealed was worse than Miyamoto's darkest estimates. Before we continue with what Lieutenant Commander Miyamoto discovered next, I want to hear from you. What's the most surprising WWII technology you've learned about? Drop a comment below and let me know where you're watching from. And if you're finding this technical analysis fascinating, hit that like button. It helps more history enthusiasts discover these stories. The intelligence report contained information from multiple sources: intercepted American technical communications, reports from neutral observers in the United States, and assessments from Japanese embassy staff before diplomatic relations severed. What it described seemed impossible. The Massachusetts Institute of Technology had established something called the Radiation Laboratory in November 1940, specifically to develop advanced radar systems. This wasn't a small military research facility. It was a massive civilian-military collaboration employing over 4,000 scientists and engineers by 1942, including many of America's most brilliant physicists. Miyamoto read the details with growing disbelief. The radiation lab had a budget of $3 million per month, equivalent to Japan's entire annual radar research budget. It occupied 140,000 square feet of laboratory and manufacturing space. It operated 24 hours per day in 3 shifts. It had dedicated machine shops, testing facilities, and prototype production lines. The lab had developed not one radar system, but dozens: air search radars, surface search radars, fire control radars, airborne intercept radars, gun-laying radars, each optimized for specific tactical applications. The SCR-268 that Miyamoto had examined was one of the older designs developed in 1940. Current American radars were even more advanced, but what made this truly impossible was the cavity magnetron. British scientists had invented this device in 1940, then shared the technology with America under the Tizard Mission Technology Exchange. The cavity magnetron generated high-power microwave radiation efficiently, enabling short-wavelength radar with exceptional resolution. Miyamoto had struggled for 2 years to develop a working magnetron that could produce 1 kilowatt at 10 centimeters wavelength. Japan's best magnetrons in late 1942 produced 500 watts in laboratory conditions, with reliability measured in hours. The Americans were mass-producing 10 kilowatt magnetrons with hundreds of hours operational life, installed in thousands of radar systems. "Why couldn't we do this?" Miyamoto asked Ito. "I understand the theory, I know what's required. Why did we fail where they succeeded?" Ito had the intelligence file open. Precision manufacturing. The cavity magnetron requires machining tolerances of 0.01 millimeters, surface finish of 0.5 microns, and vacuum sealing that maintains 10^7 torr. American industry can produce these specifications in mass production. We can barely achieve them in laboratory conditions, with hand-fitting and individual adjustment. The report detailed American manufacturing capability that seemed fantastical. The Raytheon company alone was producing 2,600 cavity magnetrons per day by mid-1942, per day. Japan's total magnetron production in 1942 was approximately 150 units, most of which failed in field conditions. The Americans had solved every technical challenge Japan still struggled with. Temperature stability. American magnetrons operated reliably from 40 degrees C to plus 60 degrees. Japanese units required temperature-controlled enclosures. Vibration resistance. American systems functioned normally under 5G acceleration. Japanese systems needed shock mounting and still failed frequently. Humidity resistance. American radars operated in tropical conditions without degradation. Japanese electronics suffered catastrophic failure in the humid South Pacific environment. Miyamoto examined the list of radar types the Americans had fielded. SCR-268 for anti-aircraft direction, SCR-270 for long-range air search, SCR-517 for airborne search, SCR-584 for precision gun laying, SG surface search for ships, Mark IV fire control for naval guns, ASV Mark II for submarine detection, dozens of specialized systems, each optimized for specific tactical applications. Japan had 4 operational radar types: Type 21 air search, Type 22 surface search, Type 13 early warning, and experimental fire control systems still in development. The Americans had developed more radar variants in 2 years than Japan had in its entire radar program. "Sir," Miyamoto said, "even if we assign every scientist and engineer in Japan to radar development, even if we mobilize every electronics factory, we cannot match this. The Americans started earlier, invested more, and achieved breakthroughs we can't replicate with current industrial capability. The magnetron alone requires vacuum tube manufacturing technology we won't develop for years." Ito closed the file. "Write your technical assessment. Compare our systems to theirs. Calculate the performance gap in each category. The High Command needs to understand what we're facing." "They won't want to hear it," Miyamoto said quietly. "No," Ito agreed, "but we'll tell them anyway." What neither man said, but both understood: radar was just one technology. If the Americans had this level of superiority in radar development and production, what else were they doing that Japan couldn't match? What other technological advantages were hidden behind the propaganda and optimistic intelligence assessments? The answer would prove even more devastating. 2 weeks after completing his technical examination, Miyamoto received additional intelligence data from Naval High Command, compiled from multiple sources including neutral diplomats, technical journals published before American censorship, and intercepted communications. The numbers were staggering. American radar production in 1942, 58,000 units of all types. Japanese radar production in 1942, 600 units of all types. Miyamoto stared at the figures. A ratio of nearly 100.1. He checked the source citations, hoping for an error. The numbers were verified from multiple independent sources. The Americans were producing in 1 week what Japan produced in an entire year. The breakdown by type was equally devastating. SCR-268 anti-aircraft radars, 3,200 units produced in 1942, deployed to every American air defense installation in the Pacific, Europe, and continental United States. Japan's equivalent Type 4 radar, 35 units produced, still in field trials, not deployed operationally. SG surface search radar for ships, 1,800 units produced in 1942, installed on every American destroyer, cruiser, and battleship, plus most large merchant vessels. Japan's Type 22 surface search radar, 120 units produced, installed on only capital ships and newest destroyers, most Japanese warships still blind in darkness and fog. SCR-584 precision gun-laying radar, 1/400 units produced in 1942. This system could automatically track aircraft and direct anti-aircraft fire with unprecedented accuracy. Japan had nothing comparable, still in early development of fire control radar concepts. Airborne intercept radar, 3,400 units produced in 1942, installed in American night fighters, enabling air-to-air combat in total darkness. Japanese night fighters relied on visual detection, effectively blind at night, except under ideal moonlight conditions. The cumulative effect was overwhelming. Every American warship had radar. Most Japanese warships had none. Every American air defense installation had radar. Most Japanese installations relied on visual and audio detection. American night fighters hunted with electronic eyes. Japanese pilots flew blind after dark. But radar production was just the beginning. Miyamoto reviewed data on supporting industries. Cavity magnetron production, America's monthly output in late 1942, exceeded 70,000 units, including magnetrons for radar, communications, and experimental applications. Japan's total magnetron production, approximately 12 units per month, all experimental, most failing within 50 hours of operation. Vacuum tube production, America manufactured 330 million vacuum tubes in 1942 for all applications: radar, communications, industrial electronics, consumer radios. Japan produced 28 million vacuum tubes in 1942, and most of those were for consumer radios, not military applications. The American electronics industry operated at a scale Japan couldn't approach. The intelligence report included American research and development investment. The radiation laboratory alone had spent $18 million on radar development in 1942. Japan's entire Navy technical research budget was $12 million annually, covering all technologies: radar, sonar, communications, weapons, propulsion, metallurgy, everything. Miyamoto calculated the ratios. American radar R&D spending was 1.5 times Japan's entire naval technical research budget. American radar production was 100 times Japanese production. American magnetron production was 7,000 times Japanese production. He thought about what these numbers meant tactically. In a night surface engagement, American destroyers would detect Japanese ships first, automatically track them with fire control radar, and engage with accurate gunfire and torpedoes before Japanese forces even knew enemy vessels were present. The Americans would fight from beyond visual range in darkness, with precision unachievable through human vision alone. In air defense, American radar would detect incoming aircraft at 100+ kilometers, vector fighters to intercept, guide anti-aircraft guns with automatic tracking. Japanese defenders would spot aircraft visually at 5 to 10 kilometers, scramble fighters without precise intercept vectors, fire anti-aircraft guns based on visual tracking with human errors and lag time. The report included combat results that validated these calculations. At the Battle of Midway in June 1942, American radar detected Japanese aircraft at extreme range, providing early warning that allowed American fighters to intercept at altitude advantage. Japanese carriers, with no operational radar, never detected American dive bombers until they were entering their attack runs. At Guadalcanal in November 1942, the naval battles showed the pattern clearly. American ships with SG radar won engagements decisively. American ships without radar suffered severe losses. The Japanese, with minimal radar deployment, fought blind against electronically sighted enemies. Miyamoto wrote carefully in his report, "The performance gap between American and Japanese radar technology is approximately 48 months. The production gap is essentially infinite. America produces more radar in 1 week than Japan can produce in 1 year. The industrial capacity gap cannot be closed through any realistic mobilization of Japanese resources." He paused, then added, "This assessment covers only radar technology. Intelligence suggests similar disparities exist in sonar, communications, computing, and other electronic technologies. The combined effect suggests America's electronic warfare capability exceeds Japan's by margins that eliminate tactical options based on traditional military factors such as training, determination, or tactical skill." He showed the draft report to Ito. "Sir, should I moderate the conclusions? High Command may view this as defeatist." Ito read the report twice. "The numbers are accurate, verified from multiple sources, conservative if anything." "Then don't moderate it. Our job is technical assessment, not propaganda. If they want comfortable lies, they can get those from the press office." Miyamoto submitted the report on November 12, 1942, marked Technical Assessment of Captured American SCR-268 Radar System with Analysis of Comparative Electronic Warfare Capability. It went to Naval Technical Command, which forwarded it to Naval Operations, which eventually sent copies to Naval High Command and the Office of Strategic Planning. The response came 3 weeks later. It was not what Miyamoto expected. The numbers Lieutenant Commander Miyamoto was seeing were staggering, and they painted an undeniable picture. If you're enjoying this deep dive into the industrial side of WWII, make sure you're subscribed to the channel. We release new technical analysis videos every week. And drop a comment. What aspect of WWII history fascinates you most? The technology? The strategy? The human stories? I read every comment. December 4th, 1942. Captain Ito was summoned to Naval High Command headquarters in Tokyo. Miyamoto was not invited, which Ito said was a bad sign. When they want to hear technical explanations, they invite the technical expert. When they want to rebuke the report, they summon only the senior officer. Ito returned late that afternoon, Miyamoto was in the laboratory testing Japanese Type 22 radar components when Ito entered. His expression was carefully neutral, which told Miyamoto everything. "They rejected the assessment," Miyamoto said. "It wasn't a question." Ito sat down heavily. "Admiral Fukudome called your report technically detailed but strategically pessimistic. Captain Nakahara from Strategic Planning said the production numbers must be American propaganda, inflated to demoralize Japanese forces. Commander Yamada suggested you were influenced by examination of advanced American equipment and lost perspective on overall military balance. Did you defend the report? I presented the methodology, multiple independent intelligence sources, verified technical specifications, conservative calculations. I showed the captured radar unit itself, demonstrated its capabilities. I offered to have you present detailed technical briefing." Ito paused. Admiral Fukudome declined. He said technical details weren't the issue. The issue was strategic assessment that contradicted established planning assumptions. Miyamoto felt anger rising, forced it down. What planning assumptions? That American industrial capacity, while large, is dispersed across multiple theaters and civilian production. That American technology, while advanced in some areas, lacks Japanese refinement and attention to quality. That American forces, while numerous, lack the training and spirit of Japanese forces. Therefore, tactical skill and operational excellence can overcome material disparities. And our report contradicts this. Your report demonstrates that American technology exceeds Japanese technology by margins that nullify tactical skill. That American production operates at scales that make material disparity an inadequate term. That electronic warfare capability gives Americans systematic advantages in detection, tracking, and fire control that transform combat mathematics. Ito looked at Miyamoto directly. Yes, your report contradicts every comforting assumption the High Command uses to justify continued offensive operations. What did they do with it? Filed under technical assessments, radar development program reference material, not distributed to fleet commands, not included in strategic planning documents, not used to modify operational plans. Miyamoto was silent for a moment. We told them the truth, we documented everything. We showed them what we're facing, and they filed it away. They don't want truth, Ito said quietly. They want validation. They want reports that confirm Japan can win through superior spirit and tactical excellence. Your report says Japan cannot win because the industrial and technological gap is too large. Therefore, your report must be wrong because the alternative is unacceptable. So we continue operations based on false assumptions. We continue operations based on Bushido spirit and operational excellence, Ito corrected, irony heavy in his voice. And when those operations fail, due to American radar giving them tactical advantages we can't counter, the failures will be attributed to individual commanders' inadequacies, not to systematic technological inferiority. Miyamoto pulled out the technical file on the SCR-268. This radar represents a 48-month technology gap. The Americans developed it 3 years ago. They've produced thousands. They're currently deploying even more advanced systems. We're struggling to field our first operational radars that approach their 1940 technology. In 3 years, where will they be? Where will we be? The High Command believes we'll close the gap through dedicated effort and superior Japanese engineering skill. The gap is widening, not closing. American radar production increased 400% from 1941 to 1942. Japanese production increased 60%. Every month they pull further ahead in absolute capability and in production scale. Ito stood. Write those conclusions in your project notes. Don't submit them officially. Continue developing the best radar systems Japanese industry can produce. That's our job. Make the best of what we have, not tell the High Command what they don't want to hear. And when American radar superiority causes more defeats, we'll examine the captured systems, document the technical gaps and file reports that will be archived without action, just as we did this time. Ito walked to the door, then turned back. Lieutenant Commander Miyamoto, you did excellent technical work. Your report is accurate, thorough, and professionally written, none of which matters because it tells a truth the High Command cannot accept. Welcome to strategic planning in wartime. After Ito left, Miyamoto sat alone with the American radar components spread across his workbench. The numbers didn't lie. The specifications didn't care about Japanese spirit. The industrial production capacity was objective reality. And none of it would change Japan's strategic planning because the truth was too painful to acknowledge. He wondered how many other officers, in how many other technical fields, had filed similar reports that were archived and ignored. How many accurate assessments of American industrial and technological superiority had been dismissed as pessimistic, defeatist, or propaganda? The answer he would learn after the war was many, far too many. March 1943. Miyamoto examined another captured American radar, recovered from a B-24 Liberator shot down near Rabaul. The SCR-117 airborne search radar showed the same pattern: superior performance, mature design, mass production quality. Operating frequency, 515 MHz. Detection range, 75 kilometers for surface submarines, 150 kilometers for ships, 30 kilometers for aircraft. Japan had no equivalent airborne radar. Japanese maritime patrol aircraft searched visually. Effective range 15 kilometers in ideal conditions. Combat reports from the Solomon Islands validated every prediction in Miyamoto's November report. American destroyers with SG radar dominated night engagements, detecting Japanese forces first, engaging from beyond visual range. At the Battle of Empress Augusta Bay in November 1942, American radar detected Japanese ships at 35 kilometers, allowing perfect tactical positioning before Japanese lookouts spotted anything. The Japanese task force was defeated decisively, losing 1 light cruiser and 1 destroyer, with 3 ships damaged against minimal American losses. June 1943. Intelligence reported American deployment of SCR-584 gun-laying radar integrated with proximity-fused anti-aircraft shells. The combination was devastating. Radar tracked aircraft automatically with 0.1 degree accuracy. Fire control computers calculated precise firing solutions. Proximity fuses detonated shells when passing within lethal radius of targets. Japanese aircraft losses to anti-aircraft fire increased by 300% in areas where Americans deployed this system. Miyamoto's report had predicted this exactly. Integration of radar tracking with automated fire control will produce anti-aircraft effectiveness that exceeds visual optical systems by factors of 5 to 10. The High Command had filed that assessment under overly pessimistic. The actual combat results showed Miyamoto's predictions were conservative. July 1943. The Battle of Kolombangara demonstrated radar superiority with brutal clarity. Japanese cruiser Jinsu, equipped with Japan's newest Type 22 radar, detected American forces at 21 kilometers. Jinsu's radar operators reported contact. Gun crews prepared for engagement. But American destroyers, carrying SG radar with 30-kilometer range, had detected Jinsu first, tracked it continuously, and maneuvered into optimal firing positions while Japanese forces were still preparing. American torpedoes struck Jinsu amidships at 0112 hours. The cruiser exploded, killing 482 men. The battle report noted dryly, "Our radar functioned as designed. Enemy radar functioned better." Miyamoto examined Japanese radar production statistics for the first half of 1943. 340 units of all types, slightly more than half the entire 1942 production. He compared with American production estimates, 62,000 radar units in the first half of 1943, accelerating beyond 1942's pace. The production gap hadn't closed, it had widened. America was now producing 180 times more radar than Japan, up from 100 times the previous year. Worse, Japanese radar quality was declining. Material shortages forced substitution of inferior components. Copper for waveguides was increasingly scarce, replaced by aluminum that corroded in tropical humidity. Precision ball bearings were prioritized for aircraft engines. Radar systems received crude sleeve bearings that introduced vibration and reduced accuracy. Vacuum tubes failed at increasing rates as quality control degraded under pressure to meet production quotas. American radar, meanwhile, maintained or improved quality while production skyrocketed. Captured units from mid-1943 showed refined designs, improved reliability, better weatherproofing. The Americans were investing their abundant resources into continuous improvement, while Japan struggled to maintain minimal production with declining quality. August 1943. Miyamoto was assigned to examine radar equipment salvaged from the battleship Mutsu, which had suffered a catastrophic magazine explosion in Hiroshima Bay. Mutsu had been fitted with Type 21 air search radar, one of Japan's most advanced installations. The radar had functioned for approximately 140 hours total operation before Mutsu's destruction. During that time, maintenance logs recorded 18 component failures requiring technician intervention, 5 complete system failures requiring replacement of major assemblies, and persistent issues with bearing vibration, power supply instability, and water intrusion. He compared with maintenance logs from captured American radars. The SCR-268 he'd examined in October 1942 had operated for 186 hours before the aircraft was lost, with 0 component failures recorded. An SG radar salvaged from a beached American destroyer showed 340 hours operation with 3 minor vacuum tube replacements, all completed by ship's electricians without specialized training. The contrast was absolute. American radars worked reliably in field conditions with minimal maintenance. Japanese radars required constant attention from skilled technicians and still failed frequently. This wasn't a performance gap that training could overcome. This was systemic difference in design maturity and manufacturing quality. November 1943. Miyamoto attended a technical conference where officers from various research commands presented developments. A submarine commander reported that American aircraft were detecting surface submarines at night, in conditions where visual detection was impossible. They must have airborne radar, the commander said. We surface at night to recharge batteries and they find us anyway. We've lost 7 boats in the last 2 months to night air attacks. Miyamoto thought of the SCR-517 airborne radar he'd examined in March. Detection range for surface submarines, 75 kilometers. He'd reported that capability 8 months ago. The prediction was now validated in blood. 7 submarines, perhaps 350 men, lost because Japan couldn't counter technology it couldn't match. Everything in Miyamoto's November 1942 report was coming true. Every prediction, every warning, every calculation of American advantages and Japanese vulnerabilities. And none of it had influenced Japanese strategy, because the truth was filed away, marked too pessimistic to distribute. August 1945. The war was over. Lieutenant Commander Miyamoto, now working in the Naval Demobilization Office, was summoned to meet with American naval intelligence officers. They had questions about Japanese radar development. Commander Robert Page, U.S. Navy, led the interrogation. You examined a captured SCR-268 in October 1942, Page said, reading from a file. You submitted a technical assessment comparing American and Japanese radar capability. We found your report in archives. It was remarkably accurate. Miyamoto said nothing. Your report calculated a 48-month technology gap between American and Japanese radar. You estimated American radar production at 100 times Japanese production. You predicted American radar superiority would provide decisive tactical advantages in night combat, air defense, and submarine warfare. Page looked up. Every assessment was correct. Some were conservative. Our production advantage was actually higher than you calculated. The report was filed as too pessimistic, Miyamoto said quietly. It didn't affect strategic planning. Page pulled out production statistics. Total American radar production, 1941-1945, 630,000 units. Total Japanese radar production, 1941-1945, 3,200 units. Ratio, 197.1. Your 1942 estimate of 100.1 was actually optimistic from Japan's perspective. The numbers were devastating. Nearly 200 times more radar production. Miyamoto had tried to warn his superiors about 100.1. The reality was twice as bad. Cavity magnetron production, Page continued. America produced approximately 2.5 million cavity magnetrons during the war. Japan produced fewer than 1,000, most of which failed in field use. Radio proximity fuses. America produced 22 million units. Japan developed none. Fire control radar. America deployed 10,000 plus units. Japan fielded fewer than 100. Miyamoto absorbed the numbers in silence. He had known Japan was behind. He hadn't fully grasped how far behind. "There were others like you," Page said. "We've interviewed dozens of Japanese technical officers. Many submitted reports documenting American technological and industrial superiority. Almost all reports were archived without action, dismissed as pessimistic or defeatist. One officer said his report on American shipbuilding capacity was returned with a note saying the numbers must be wrong because they implied Japan couldn't win a naval war. The numbers weren't wrong." "No," Miyamoto said. "The numbers were never wrong." Page closed the file. "Your technical assessment of the SCR-268 was the most accurate analysis of American radar capability we found in Japanese archives. It should have influenced your Navy's strategic planning. Why didn't it?" Miyamoto considered the question because it told a truth that contradicted the assumptions necessary to justify continuing the war. If our leaders accepted that American technological and industrial superiority was too large to overcome, they would have to question the entire strategy. Instead, they filed the reports and continued operations based on belief in Japanese fighting spirit and tactical excellence. "But fighting spirit doesn't defeat radar," Page observed. "No," Miyamoto agreed. "It doesn't." After the interrogation, Miyamoto walked through Tokyo's ruins. He thought about the SCR-268 he'd examined in October 1942, the numbers that told an undeniable truth, the report that was filed and forgotten. He wondered how many lives might have been saved if that truth had been accepted instead of archived. How many cities might stand intact if industrial and technological reality had influenced strategy rather than ideology? The numbers had never lied. Radar didn't care about spirit. Industrial production followed mathematical laws, not wishes. And Japan had fought a war against objective reality, which is a war no nation can win. The historical record proved Lieutenant Commander Miyamoto right in every detail. If this kind of detailed technical history interests you, you'll love our other videos analyzing WWII equipment and strategy. Check out the playlist in the description. And before we wrap up with the bigger lesson here, hit that like button if you appreciate this level of research and detail in history content. The story of Takeshi Miyamoto and the SCR-268 radar is a microcosm of a larger failure. The collision between objective reality and ideological commitment. Miyamoto was not unique. Throughout the Japanese military and technical establishment, competent officers recognized the scale of American industrial and technological superiority. And throughout that same establishment, their assessments were systematically ignored. Commander Tamichi Hara, the only Japanese destroyer captain to survive the entire war, wrote in his post-war memoir about the growing realization among Japanese officers that our night-fighting expertise had become obsolete due to American radar superiority. His wartime reports about American technological advantages were dismissed as defeatist. Captain Mitsuo Fuchida, who led the Pearl Harbor attack, later documented his 1943 assessment that Japan's shipbuilding and aircraft production couldn't match American replacement rates. His report was archived without distribution to operational commanders. Engineer Jiro Horikoshi, designer of the Zero fighter, submitted analyses showing that American fighters were rapidly surpassing the Zero in speed, firepower, and armor protection. His recommendations for radical redesign were rejected as requiring resources Japan couldn't spare. The pattern was consistent. Technical experts examined the evidence, calculated the disparities, and reported conclusions that contradicted official assumptions. The reports were acknowledged, filed, and ignored. Not because the High Command doubted the technical accuracy, but because accepting the conclusions would require abandoning strategic commitments already made. This is the mechanism of institutional failure in war, when ideology takes precedence over reality, when comforting assumptions matter more than uncomfortable facts, when the cost of admitting error exceeds the cost of continuing failed policies. Japan's High Command had committed to a strategy premised on rapid victories achieved through superior training and tactical excellence. Evidence that this strategy couldn't succeed against overwhelming American material and technological superiority was therefore unacceptable, regardless of its accuracy. The consequences were inevitable. Reality doesn't negotiate with ideology. Industrial capacity follows economic laws, not propaganda narratives. Radar detection range is determined by physics, not fighting spirit. Japan continued operations based on assumptions that competent technical officers had already disproven, fighting a war that careful analysis had shown couldn't be won. The tragedy is that the truth was known. Officers like Miyamoto had documented it thoroughly, submitted it through proper channels, presented it with meticulous evidence. The information existed. It was simply ignored, because the alternative, accepting defeat or negotiating peace from weakness, was ideologically impossible. Miyamoto's examination of the SCR-268 radar on October 15, 1942, revealed not just American technological superiority, but Japan's systemic inability to accept inconvenient truths. The radar specifications told him Japan was fighting a war it had already lost industrially and technologically. The High Command's response to his report told him Japan would continue that war regardless, because admitting the truth was more threatening than facing the reality. In the end, the numbers proved correct. Radar didn't lie. Industrial production followed its own mathematics, and Japan fought on for 3 more years, accumulating losses that careful technical analysis had predicted, based on assumptions that objective reality had already invalidated. The lesson extends beyond one nation's wartime failure. Whenever institutions prioritize ideology over evidence, comfort over truth, commitment over reassessment, the pattern repeats. Reality always wins eventually. The only question is, how much is lost before the truth becomes undeniable? Thank you for watching this deep dive into one of World War II's most revealing technical stories. The examination of captured American radar wasn't just about technology. It was about the devastating consequences of ignoring objective truth in favor of comforting assumptions. If you found this analysis compelling, there's another fascinating story waiting for you on screen right now about technological decisions that shaped the war's outcome. Click to continue exploring the hidden technical battles that determined history. And remember to subscribe so you never miss these detailed historical investigations. Until next time, keep questioning, keep learning, and never stop seeking the truth behind the headlines.